for the position tolerance. The goal of this lesson is to interpret special applications of the position tolerance. When you're finished with this lesson, you should be able to describe the term projected tolerance zone, describe a real-world application of the projected tolerance zone modifier, interpret a position tolerance using the projected tolerance zone modifier, describe how a position tolerance with the projected tolerance zone modifier can be verified, describe what a multiple single-segment position tolerance is, describe a real-world application of a multiple single-segment position tolerance, interpret a multiple single-segment position tolerance, describe what a composite position tolerance is, describe a real-world application of a composite position tolerance, interpret a composite position tolerance, interpret a position tolerance applied to a hole, MMC, at an angle to the datums, interpret a position tolerance used as a bidirectional tolerance, interpret a position tolerance applied to an elongated hole, interpret a position tolerance used to tolerance a symmetrical relationship, interpret a position tolerance using the LMC modifier, interpret a position tolerance used to tolerance the spacing and orientation of a hole pattern, explain what zero tolerance at MMC tolerancing is, list 3 benefits of zero tolerance at MMC dimensioning, describe a real-world application for using zero tolerance at MMC, interpret a zero tolerance at MMC position application. It will take approximately 40 minutes to complete this lesson. These are the new terms introduced in this lesson. It's important for you to know these terms in order to understand advanced position tolerance applications. On the left, you can see the default tolerance zone for a position tolerance. The tolerance zone exists for the length of the toleranced feature. A projected tolerance zone is shown on the right. A projected tolerance zone is a tolerance zone that is projected or moved outside the feature of size. The height that the tolerance zone is projected must be specified. Notice how the projected tolerance zone reduces the orientation deviation of the tolerance feature without reducing the location deviation. A projected tolerance zone should be considered for use where the orientation deviation inside a position tolerance zone could result in interference with the mating part. One real-world application is in bolted joint assemblies, where the thickness of the part with the clearance hole is greater than the depth of the threaded hole. Take a look at the figure on the left. Without a projected tolerance zone, the orientation deviation of the fastener may result in an interference condition with the mating part. A projected tolerance zone is used restricting the orientation of the fastener, but not the location, to ensure assembly with the mating part on the right. In the figure on the right, you can see that using a projected tolerance zone permits the use of the largest position tolerance while eliminating the risk of the orientation deviation that would create an interference condition. The height of a projected tolerance zone should be equal to the maximum height of the mating part. The axis of the hole must reside in the projected tolerance zone. Since the height of the projected zone is longer than the depth of the hole, the orientation deviation of the hole is more restricted than the location deviation for the hole.
A projected tolerance zone exists outside the extent of the toleranced feature of size. You're correct. A projected tolerance zone is used when it is important to restrict the location of a hole. You're correct. Click the right arrow to continue.
The drawing shown here is an example of how to specify a projected tolerance zone in a position tolerance. Note the use of the projected tolerance zone modifier and the specification of the projected tolerance zone height in the feature control frame. The height of the projected tolerance zone should be equal to the maximum thickness of the mating part. The drawing on the left shows a position tolerance with the projected tolerance zone. The interpretation for the position tolerance is on the right. The projected tolerance zone is shown in yellow. In this application, the following conditions apply. The tolerance zones are fixed size cylinders of 0.5 diameter. The tolerance zones are projected to a minimum height of 15 from datum plane A. The tolerance zones are perpendicular to datum plane A. The tolerance zones are located at the true position of the holes. The axis of the unrelated actual mating envelope must be within the tolerance zone. The tolerance zones limit the location, spacing, and orientation of the holes. No additional tolerance is allowed as the holes get larger. Each hole must be within its size limits. You can easily verify a projected tolerance zone using a gauge pin threaded into the hole. The length of the pin protruding from the hole is equal to the projected height. The axis of the pin represents the axis of the unrelated actual mating envelope of the fastener passing through the mating part. You can measure the portion of the pin protruding out of the hole using a CMM. If the axis of the pin lies within the projected tolerance zone, the part passes. If not, the part fails.
The specified height of a projected tolerance zone is the maximum height of the tolerance zone. You're correct. One common method for verifying a projected tolerance zone is to use a gauge pin inserted into the toleranced feature of size with an extension protruding up for the height of the projected tolerance zone. You're correct. The height of a projected tolerance zone is often determined by the maximum height of the hole in the mating part. You're correct. Click the right arrow to continue.
This figure shows an example of a multiple single-segment position tolerance. A multiple single-segment position tolerance is two or more single-segment position tolerances applied to the same feature of size or pattern of features of size. You use a multiple single-segment position tolerance to define the location, orientation, and spacing of a pattern of features of size. The requirements for the location of the pattern are different from those for the spacing and orientation of the pattern. Specify the tolerance by stacking two or more individual feature control frames with their left sides aligned, as shown here. A multiple single-segment feature control frame typically contains 2 or 3 segments, but it may contain as many segments as needed for you to convey the design requirements. Each segment of a multiple single-segment position tolerance creates different tolerance requirements for location, spacing, and/or orientation of a pattern. The uppermost segment is the pattern locating tolerance. It specifies a location tolerance for the pattern of features of size relative to the datum references specified. Each lower segment may create an additional location, orientation, or spacing requirement on the pattern relative to the datum references specified and can control the location or orientation of a pattern. None of the datum references on the lower segments can be identical to those in the upper segment. If datum feature references are not specified in a lower segment, the segment only controls spacing or alignment between the features of size in the pattern. You'll often use a multiple single-segment position tolerance when the function of the part requires a tighter tolerance for the spacing and orientation of a pattern of features of size than it does for the location of the pattern. Applications may include 1. Mounting holes for cover and spacer plates. 2. Holes for switch, gauge, and light fixture mounting brackets. 3. Mounting holes for alternators, compressors, oil pumps, filters, etc.
Which feature control frame is a multiple single-segment position tolerance? You're correct. This feature control frame is a multiple single-segment position tolerance. Click the right arrow to continue.
The drawing to the left shows an example of a multiple single-segment position tolerance. The upper segment controls the location of the whole pattern. Since the MMC modifier is specified, we'll use the surface interpretation. The interpretation of the upper segment of the multiple single-segment position tolerance is shown on the right. A functional gauge is used to verify the position tolerance. In this application, the following conditions apply. The tolerance zones are 4 VC acceptance boundary cylinders of 11.2 diameter. The VC acceptance boundaries are located at the true position of the holes. The surfaces of the holes must fit around the acceptance boundaries. The VC acceptance boundaries limit the location of the holes relative to the datum reference frame. Each hole must be within its size limit. Next, we'll look at the interpretation of the lower segment of the position tolerance. The drawing on your left shows an example of a multiple single segment position tolerance. The lower segment controls the location of the whole pattern. Since the MMC modifier is specified, we'll use the surface interpretation. The interpretation of the multiple single segment position tolerance is on the right. A functional gauge is used to verify the position tolerance. In this application, the following conditions apply. The tolerance zones are 4 VC acceptance boundary cylinders of 11.8 diameter. The VC acceptance boundaries are located at the true position of the holes. The surfaces of the holes must fit around the acceptance boundaries. The VC acceptance boundaries control the location of the holes relative to datum B. The VC acceptance boundaries control the orientation of the holes relative to datums A and B. The VC acceptance boundaries control the spacing between the holes. Each hole must be within its size limit.
When the holes are at MMC, what is the maximum allowable orientation deviation of the holes relative to datum A? You're correct. When at MMC, the maximum allowable orientation deviation of the holes is 0.1. Click the right arrow to continue.
Take a look at this example of a composite position tolerance. A composite position tolerance is a feature control frame that contains multiple segments with a single entry of a position tolerance symbol that is applicable to all horizontal segments of the feature control frame. Each horizontal segment has rules for how to specify the tolerance value, modifiers, and datum feature references. A composite position feature control frame typically contains 2 or 3 segments, but it may contain as many segments as needed to convey the design requirements. A composite position tolerance can only be applied to patterns of features of size. Each segment creates different tolerance requirements for location, spacing, and/or orientation of the pattern. The uppermost segment is the pattern locating tolerance. It specifies a location tolerance for the pattern of features of size relative to the datum reference specified. Depending on the datum's reference, the uppermost segment can constrain translation and rotational degrees of freedom. Each lower segment creates an orientation or spacing requirement on the pattern relative to the datum references specified. The lower segments cannot control location. They can only constrain rotational degrees of freedom. Therefore, the lower segments can only control orientation, alignment, and spacing of a pattern. If datum references are not specified in a lower segment, the segment only controls spacing or alignment between the features of size in the pattern. There is a major difference between multiple single segment and composite position tolerances. In a multiple single segment position tolerance, each segment can constrain translational and rotational degrees of freedom, in other words, control location. In a composite position tolerance, only the uppermost segment can constrain translational and rotational degrees of freedom. The lower segments can only control rotational degrees of freedom, in other words, orientation only. You can often use a composite position tolerance on a pattern of features of size where the function of the part allows a larger location tolerance for the pattern, but requires a tighter tolerance for the spacing and orientation, usually to several datums. You can also use a composite position tolerance to control alignment between coaxial diameters to a tighter tolerance than their location or orientation. Applications may include 1. Nameplate mounting holes to control parallelism between the edge of the nameplate and the edge of the mating part. 2. Alignment between bearing bores for camshafts, crankshafts, bushing bores for linear actuators, etc. 3. Alignment between pivot holes, hinge pinholes, etc.
Which feature control frame is a composite position tolerance? You're correct. This is a composite position tolerance. Click the right arrow to continue. In which application would a composite position tolerance likely be used? You're correct. A composite position tolerance would likely be used for alignment between bearing bores. Click the right arrow to continue.
The drawing on the left shows an example of a composite position tolerance. The upper segment controls the location of the hole pattern. Since the MMC modifier is specified, we'll use the surface interpretation. The interpretation of the upper segment of the position tolerance is on the right. A functional gauge is used to verify the position tolerance. In this application, the following conditions apply. The tolerance zones are 4 VC acceptance boundary cylinders of 11.2 diameter. The VC acceptance boundaries are located at the true position of the holes. The surfaces of the holes must fit around the acceptance boundaries. The VC acceptance boundaries limit the location of the holes relative to the datum reference frame. The holes must be within their size limits. Next, we'll look at the interpretation of the lower segment of the position tolerance. An example of a composite position tolerance is shown on the left. The lower segment controls the orientation relative to datums A and B and the spacing of the hole pattern. Since the MMC modifier is specified, we'll use the surface interpretation. The interpretation of the composite position tolerance is on the right. A functional gauge is used to verify the position tolerance. In this application, the following conditions apply. The tolerance zones are 4 VC acceptance boundary cylinders of 11.8 diameter. The VC acceptance boundaries are located at the true position of the holes. The surfaces of the holes must fit around the acceptance boundaries. The VC acceptance boundaries control the orientation of the holes relative to datum B. The VC acceptance boundaries control the spacing between the holes. The holes must be within their size limits.
What is the size of the acceptance boundary that determines the spacing between the holes? You're correct. The acceptance boundary that determines the spacing between the holes is 11.9. Click the right arrow to continue.
The drawing on the left shows a position tolerance applied to a pattern of holes that are not parallel or perpendicular to the datum reference frame. The chart on the right shows the location tolerance permissible for various hole sizes. The MMC modifier is specified, so we'll use the surface interpretation. In this application, the following conditions apply. The tolerance zones are fixed size acceptance boundaries of 5.6 diameter. The acceptance boundaries are oriented 30 degrees relative to datum B. The acceptance boundaries are located and oriented at the true position of the holes. The acceptance boundaries limit the location, spacing, and orientation of the holes. Additional tolerance is allowed as the holes get larger. The holes must be within their size limits.
In this application, what does the position tolerance applied to the 8.0 diameter holes control? You're correct. The position tolerance applied to the 8.0 diameter holes controls the location, spacing, and orientation. Click the right arrow to continue.
The drawing on your left shows a part with a pattern of holes on a strip. The holes are almost as large as the width of the strip. Therefore, the spacing between the holes in the horizontal direction can vary more than the location of the holes in the vertical direction. There are 2 position tolerances applied to the hole pattern. One applies in the vertical direction, the other applies in the horizontal direction. These are referred to as a bidirectional position tolerance. A bidirectional position tolerance is where the location of a feature of size is defined with different amounts of tolerance in 2 directions. Because bidirectional position tolerances result in non-cylindrical tolerance zones, a diameter symbol is not shown in the feature control frame. The interpretation on your right shows the acceptance boundaries for the hole pattern. In this example, the following conditions apply. The tolerance zones are fixed size acceptance boundaries of 15 wide and 15.4 high. The acceptance boundaries are oriented 90 degrees relative to datum A. The acceptance boundaries are located and oriented at the true position of the holes. The acceptance boundaries limit the location, spacing, and orientation of the holes. Additional tolerance is allowed as the holes get larger. The holes must be within their size limits.
What type of position tolerance or tolerances are typically used where the function of a feature of size can have more location tolerance in one direction than another direction? You're correct. A bidirectional position tolerance is often used to control the location of a hole to a different value in each direction. Click the right arrow to continue.
The drawing on your left shows a part with a pattern of holes on a bracket. The holes are elongated holes or slots. When tolerancing an elongated hole, you'll use two position tolerances, one for the length and one for the width. Attach the feature control frames to the length and width dimensions to create a bidirectional tolerance. Do not show diameter symbols in the feature control frames. The interpretation on your right shows the acceptance boundaries for the elongated holes. In this example, the following conditions apply. The tolerance zones are fixed size acceptance boundaries of 4 wide and 9 long. The acceptance boundaries are oriented 90 degrees relative to datum A. The acceptance boundaries are located and oriented at the true position of the holes. The acceptance boundaries limit the location, spacing, and orientation of the holes. Additional tolerance is allowed as the holes get larger. The holes must be within their size limits. Where the interpretation of the position tolerance zone may not be clear for all drawing users, the keyword boundary may be specified along with the position tolerances. Boundary is an optional keyword used with position tolerances to denote that only a boundary interpretation exists for a position tolerance. In other words, there is no axis interpretation. The boundary notation is a practice from prior versions of Y14.5. The 2009 edition of Y14.5 states that the use of the MMC modifier indicates that a boundary interpretation applies and allows the use of the word boundary as an option.
When bidirectional position tolerances at MMC are applied to an elongated hole, which interpretation should be used? You're correct. The boundary interpretation should be used when the MMC modifier is specified. Click the right arrow to continue.
The drawing on the left shows a part with a symmetrical relationship. The rectangular opening on the top of the part is symmetrical with datum feature A. A position tolerance at MMC and MMB is used to control the symmetrical relationship. The interpretation on your right shows the acceptance boundary for the position tolerance. In this example, the following conditions apply. The tolerance zone is a fixed size acceptance boundary 12 wide. The acceptance boundary is oriented and centered relative to datum A. The acceptance boundary limits the location and orientation of the rectangular opening. Additional tolerance is allowed as the rectangular opening gets larger. The maximum deviation is permitted when both the rectangular opening and datum feature are at LMC and LMB respectively. The rectangular opening must be within its size limits.
When is the maximum tolerance allowed for the position tolerance? You're correct. The maximum tolerance is allowed when the toleranced feature of size is at least material condition and the datum feature is at least material boundary. Click the right arrow to continue.
This drawing shows a part with a position tolerance at LMC. The LMC modifier is often used when the functional consideration is to control a minimum distance on a part. Some examples include a minimum wall thickness or minimum machine stock on a casting. When the LMC modifier is specified, it also invokes perfect form at LMC for the toleranced feature of size. The chart on the right shows that the tolerance value stated in the geometric tolerance is the allowable tolerance when the feature of size is at LMC. When the feature of size departs from LMC towards MMC, additional tolerance is permitted. When the feature of size is at MMC, the maximum tolerance is allowed. In this example, the following conditions apply. The tolerance zone is a fixed size acceptance boundary 24.0 diameter. The acceptance boundary is oriented and centered relative to datum A. The acceptance boundary limits the location and orientation of the diameter. Additional tolerance is allowed as the diameter gets larger. The maximum deviation is permitted when the diameter is at MMC. The diameter must be within its size limits. Perfect form at LMC applies to the outside diameter. Perfect form at MMC applies to datum feature A.
Using the LMC modifier in a geometric tolerance is useful for protecting a minimum wall thickness. You're correct. Using the LMC modifier in a geometric tolerance is useful for ensuring that the worst-case part fits with the mating part. That's not the right answer. Please try again. You're correct. When the LMC modifier is used, it permits additional tolerance when the feature of size is at MMC. You're correct. Click the right arrow to continue.
The drawing on the left shows a part with a position tolerance at MMC applied to a hole pattern. The hole pattern locates the part in its assembly. The interesting item here is that the position tolerance only references a single datum perpendicular to the datum feature. In this case, the position tolerance is not controlling the location of the hole pattern. It's controlling the spacing and orientation of the hole pattern. Often, when this type of position tolerance is used, the hole pattern is designated as a datum feature. Other features are referenced to the surface as the primary datum and the hole pattern as the secondary datum. The interpretation of the position tolerance is shown on the right. Since the MMC modifier is specified, the surface interpretation is used as shown by the functional gauge. In this example, the following conditions apply. The tolerance zones are four fixed-size acceptance boundaries 7.8 diameter. The acceptance boundaries are oriented relative to datum A. The acceptance boundaries limit the spacing and orientation of the holes. Additional tolerance is allowed as the holes get larger. The maximum deviation is permitted when the holes are at LMC. The holes must be within their size limits.
A position tolerance may be applied to a pattern of holes and not control the location of the pattern. You're correct. When a position tolerance is applied to a pattern of holes, it controls the spacing between the holes. You're correct. Click the right arrow to continue.
An important element in the design of a part is how it's dimensioned and toleranced. Tight tolerances don't guarantee a quality part, only an expensive one. A dimensioning method that protects the part function and helps to reduce cost is called zero tolerance at MMC. Zero tolerance at MMC appears restrictive to anyone not familiar with the benefits and concepts of GD&T. However, once the method is understood, it becomes apparent that using this method protects the part function and offers the maximum flexibility for manufacturing. Zero tolerance at MMC is a dimensioning method that takes the tolerance stated in the feature control frame, combines it with the size tolerance, and states a zero tolerance in the feature control frame. You should consider the use of the zero tolerance at MMC method wherever the function of the toleranced feature is assembly. Although the zero tolerance at MMC is shown with position tolerances, it can be used with any geometric tolerance that is applied at MMC. There are three primary benefits of using the zero tolerance at MMC method. First, it provides flexibility for manufacturing. Second, it prevents the rejection of usable parts. Finally, it reduces manufacturing costs. The benefits of zero tolerance at MMC can have a significant impact in an organization.
One benefit of the zero tolerance at MMC concept is that it prevents the rejection of usable parts. You're correct. A zero tolerance at MMC should only be used on position tolerances. You're correct. Click the right arrow to continue.
The zero tolerance at MMC method should be considered for use wherever the function of the tolerance feature or features of size is assembly. Two examples are clearance holes for fasteners in a bolted joint assembly and mating features of size.
For what function is the zero tolerance at MMC concept recommended? You're correct. The zero tolerance at MMC concept is recommended for assembly. Click the right arrow to continue.
The drawing on the left shows a part with a conventional position tolerance of 0.3 at MMC. On the right, the same part is dimensioned with zero tolerance at MMC. The 0.3 tolerance has been removed from the feature control frame and combined with the size tolerance. Note that the functional parameter, the virtual condition of the holes, is the same for both dimensioning methods. The tolerance is also the same. You can visualize the effects of a position tolerance through the use of a tolerance analysis chart. A tolerance analysis chart is a chart that graphically displays the available tolerances of a feature of size as defined by the drawing specifications. The tolerance analysis chart on your left shows the available tolerances for the holes from the conventional tolerancing example from the previous screen. The allowable measured position deviation is shown on the vertical axis. The hole size and virtual conditions are shown on the horizontal axis. The shaded area of the chart represents the acceptable parts. The dots, labeled 1 through 4, represent hole measurements of 4 parts shown in the table on the right. 3 of the 4 parts would be rejected on the basis of the hole size not being within the drawing specifications. Even though the parts would assemble, they're rejected because their hole sizes do not meet the print specification. The tolerance analysis chart on your left shows the available tolerances for the holes from the zero tolerancing at MMC example from page 40. The allowable measured position deviation is shown in the vertical axis. The hole size and virtual condition are shown in the horizontal axis. The shaded area of the chart represents the acceptable parts. With the zero tolerancing at MMC method, the zone for part acceptance is increased by making the MMC size equal to the virtual condition of the holes. Once again, the dots labeled 1 through 4 represent hole measurements of 4 parts shown in the table on your right. These are the same parts that we used in the conventional tolerancing example. This time, when you compare the same 4 parts to the acceptance limits, all 4 parts would be accepted. When dimensioning holes, if their function is assembly, you should consider using the zero tolerance at MMC method. With this method of dimensioning, functional parts are not rejected, and more flexibility for manufacturing results in lower costs. This chart shows a comparison of parts accepted and rejected using conventional tolerancing and zero tolerancing at MMC.
If the position tolerance on this drawing was converted to use the zero tolerance at MMC method, what would the size tolerance of the holes be revised to? You're correct. The position tolerance would be subtracted from the MMC size tolerance. The size of the holes would be revised to 7.7, 8.4. Click the right arrow to continue.
These topics are recommended for further study to improve your understanding of advanced position tolerance applications. You've just completed the lesson on position tolerance special applications. If you're not confident in your understanding of these topics, review the information before proceeding. Close this window to exit the lesson.